Yeah, so this is my third talk, but this is the second lecture series, which is completely, I think it's completely independent of the first two lectures. Well, we'll see. So, all right, so I'm going to be talking about Selmer groups, and, well, you can talk about these for any abelian variety over any global field, but I'm going to stick to the global field being Q. And so let me just first start by setting up some notation associated to the field Q. So G will be the absolute Galois group. And, well, QV will be the completion of Q at a place V. So that's going to be either real numbers, if V is the infinite place, or else it'll be QP if V is equal to P. Okay, so p-adic numbers. And then you can also define the ring of Adels, which is the restricted direct product of these QVs with respect to the subrings ZV, so which makes sense for all the finite V's. And then, so by definition, that means you take all the possible elements of the direct product such that the element belongs to the subring, is v-adically integral for all but finally many. Okay, so, all right, so that's the notation for the associated to Q. And now we're going to take an elliptic curve over Q. And we want to know what the group of rational points looks like. And so the first thing to say is, well, there's Mordel's theorem. So Mordel's theorem says that the group of rational points is finitely generated. And there's only one known proof of this. Well, essentially one known proof. And so the only, up to some minor variance. So the only known proof is to, well, you start, there are two ingredients. One is called the weak, well, I guess it'd be the weak Mordell theorem. So the weak would be, which would say that if you take this group modulo n times it, then that's finite for some n greater than or equal to 2. And the other, and so, okay, once you have that, then you need a little extra ingredient involving height functions to go from this to knowing that the whole group is finally generated. Okay, so I'm not going to talk about height functions at all. I want to focus on the first part of this. So why is that true? Why is E of Q mod and E of Q finite? And, well, for that, you start with the exact sequence of Galois modules that so involving the multiplication by n map on the elliptic curve. So okay, so here when I write this, you can think, I mean, you can either think about sheaves in the atoll site of E or something, but maybe you prefer to think in just take the q bar points of E and think of that as a module with Galois action. That's maybe nicer. So okay, so let's just think of these. So when I write E, you can imagine that this is just the set of q bar points here as an abelian group with the action of the group G on it. Okay, and so then if you take G invariance, and the reason for taking G invariance is that we want to know not E of Q bar, but we want to know E of Q. Then what do you get? So you get a long, well, you start out by getting, I mean, taking G invariance is a left exact functor, so you'll start out by getting this. And it looks like it's good news because it looks like it's telling you something about the map, the multiplication by n map on E of Q, whose co-kernel is what we're trying to bound. And unfortunately, it's not exact, so things do not end here, and you have to use cohomology. And so the next thing, so that's the whole point of cohomology. Okay, so you can continue this sequence. And it keeps going after that. Yeah, so when I write something like H1Q comma E, that's sort of an abbreviation for H1 of the absolute Galois group of Q acting on the Q bar points. Okay, which And okay, so if from this exact sequence, well, you can truncate it by sort of cutting off the beginning of the sequence and replacing this group by the co-kernel of this multiplication by n map. And so if you do that, then what you end up getting is this. You have 0 goes to e of q mod n e of q, and then okay, so that goes into this next this h1, which then goes to the h1 qe, and you can okay, so all right, so this is, well, it looks nice because now you're getting this group that you're interested in inside this Gauss cohomology group. Well, it'd be nice if this thing in the middle were finite, because then, well, if that's finite, then that'll be finite. Unfortunately, though, this group in the middle is always infinite, and so it's not very good for proving finiteness of that first group. So what you would want, so what you need to do is now say some extra words in order to control the image of this first map in order to prove the finiteness of this. And the way to do that is by looking at local constraints. So you can do the same. So far I haven't really used the fact that my ground field is Q. Everything, all this stuff would work pretty much over any field. Well, maybe perfect if you want to do it. If you want to talk about Q bar instead of Q separable or something. But anyway, so you can do that. You can write down exactly the same sequence for any completion of Q, for example. So let's do that. So let's write E of now QV mod n E of QV. I'll just copy that sequence, and then H1 of the absolute Gauss group of QV, which is that's going to be a decomposition group inside the Gauss group there. So okay, so you have a sequence like this, and well, you can do this not just for one V, but you can do this for all V. So you can take a direct product over all the different places. And then there are maps, there are vertical maps that go this way. So it's either the obvious map here, mapping E of Q into E of QV, or else it's a restriction map of Gauss cohomology. Okay, and actually you can do a little bit better. You can instead of taking the direct product, you can also take restricted direct products, and that'll be important for something I say later on. So you can replace these by subgroups, because the E of Q will map not only into E of QV, but so let me now put the restricted direct product here. I guess really to define this, you have to say what you'd have to also define the corresponding sequence over ZV, and well, okay, there are different ways to do that. One way is to use étale cohomology here. Let me not worry too much about that, but there is an analogous sequence over ZV for almost, at least for all the good V's. So that'll be good enough. And let me just so that I can I don't have to write this restricted direct product all the time. I'm going to use an abbreviation. I'll define E of the Adels modulo n times it to be this, and similarly I'll use analogous notation here. This will be H1 of Adels comma E bracket n, and this will be H1 of the Adels bracket comma E. Okay, so all right, so what's the point? So I'm trying to bound the image of this map, and one thing I can say is if I have something here that comes from here, well, then when I look at it locally, when I map it down here, it better come from locally from local points here. So if I label these maps alpha and beta, and well, while I'm at it, let's also label this one. Let's call this one gamma. I can now define a subgroup of that contains the image of E of Q mod n E of Q. Yeah, so this is going to, so I'm using this, I can now define the Selmer group. So the Selmer group is going to be, the n Selmer group of E is a subgroup here. So the Selmer group is, one thing that's, it's not the set of locally trivial elements. It's not the set of things here that are in the kernel of beta. What what I want to define it as instead is it's the set of things here that when you map them down to here, they're in the image of alpha. Because those are the ones, in other words, I take the things, I want to know what's globally in the image, but that's hard to answer, that's hard to figure out what those are. So instead I'll ask something weaker, look at the elements here that are locally in the image of points on the elliptic curve. Okay, so that means that I'm going to define this as the inverse image under beta of the image of alpha. Yeah, so they're the set of things here that map down into the image. Okay, so that's, yeah, and the point of this is that this group, just by the commutativity of the diagram, that's going to be an upper bound for, well, for E of Q mod any E of Q. And also by using some standard theorems of algebraic number theory, you can, so like finiteness of the class group and stuff like that, you can prove that this group is finite. And not only is it finite, but in principle, it's computable. So this gives you a way to compute an upper bound on the rank of an elliptic curve by computing that Selmer group. Okay, so and then so that's one group you can define using this diagram. Another one is the Tate-Shafarevich group. So that's sometimes also called the Shafarevich-Tate group, depending on. I've been told that if you alphabetize them, then, well, it depends on which language you're using. Because in English, well, Shafarevich comes before Tate in English, but in the Cyrillic alphabet, T comes before Shah. The Shah is that's the first letter of Shafarevich's name. So, and yeah, so this is defined to be the kernel of the last vertical map. So in other words, they're the cohomology classes here that are locally trivial. Yeah, and you can, if you want, you can interpret that in terms of principal homogeneous space as well, since this H1 Q, E parameterizes principal homogeneous spaces under E. All right, so okay, so we're going to study the Selmer group, and the reason we're interested in Selmer group is that is because it's giving you some bound on the rank, and so by bounding, by understanding the distribution of the Selmer group, you can understand the distribution of ranks of elliptic curves. And so yeah, but we're not going to just look at one E at a time. We're going to ask what happens as E varies over all elliptic curves over Q. So yeah, so what happens in all this if we now vary E? And look statistically at what happens to the Selmer group. Well, in order to talk about this, I mean, there are countably many elliptic curves, so you can't really talk about probability in the sense of a probability space, but you can talk about density in the same kind of way we talk about for square-free integers and so on. And in order to do that, you have to order the elliptic curves. I mean, there's a natural way to order positive integers, so it's pretty clear how you should count those. But for elliptic curves, what are you going to do? Well, you want to order them in some way. And so you need to measure, well, how are you going to order them? Well, you can define some notion of size or height for the elliptic curve. So let's do that. So I'll just use a naive height where you just take, well, you write down some equation for it using an A and a B, and you just do something like this. So where it says where E is, yeah, so this is, so okay, so let's say where E is this elliptic curve, and where the A and the B are integers, and they're sort of minimal in some sense. So you don't, I mean, which concretely means that there's no prime such a P the fourth divides A and P the sixth divides B, because otherwise you could do some change of variable to get rid of that factor. So okay, so you put E in some sort of minimal short Weierstrass form, and then based on those coefficients, you can define this height. And then you have only finitely many elliptic curves up to any given height, and so you can count. So now you can define density using this. So all right, so let's say let me use the script E to denote all the elliptic curves over Q, and then E sub less than X will be defined to be the set of elliptic curves over Q of height up to X. And so now, in terms of those, I can define density. If I have any subset of elliptic curves, which you can think of as an event if you want, it's a language of probability, then you can define its density or probability that happens to be the limit as x goes to infinity of, well, you take all the elliptic curves of height up to x, you count how many there are, and then you count among those how many satisfy the property. So it should be this. Okay, so that's a notion of density. And so what's the question now? Well, let's talk about P Selmer groups, or P is a prime. So given P, what is the distribution of the Selmer group? Well, I mean, the P Selmer group is going to be just an FP vector space. So all you can really ask about it is, what is its dimension? So the question is, what's the probability that its dimension is equal to some particular integer? Yeah, so maybe given P and an integer S, what is the probability that the dimension of the P Selmer group of a random elliptic curve over Q is equal to this little s? Okay, so that's the kind of question that we want to answer. Okay, so the answer is going to be that the P Selmer group acts as if it were an intersection of two maximal isotropic subspaces of an infinite dimensional quadratic space. So in order to make sense of all those words, I have to tell you what they are, what they mean. So let me start by talking about maximal isotropic subspaces. Well, and then once I tell you what all these things mean, then I'll also have to tell you why these have anything to do with elliptic curves. So, okay. Okay, so forget everything now, and we'll just start over. No elliptic curves. There's just a vector space. F is going to be a vector space over Fp, and it'll be of dimension 2n. And then I'll also take a quadratic form on that vector space, and that quadratic form will just be this standard one, where I take, well, I mean, there are 2n variables, and what is its value on a vector in V? It's just this kind of inner product type of quadratic form. So you just take, so it's a quadratic form in all 2n variables, and, well, that's okay, so it's non-degenerate. And when you take this vector space with this quadratic form, well, that's called a quadratic space. And this is a very particular quadratic space. It's called a hyperbolic. When you have a quadratic space that's isomorphic to this one, it's called a hyperbolic quadratic space. Okay. And also, I mean, this Q, it also gives rise to a symmetric bilinear form. So, bilinear pairing, let's say, bilinear pairing. So, what is this pairing? So, I mean, this is just the standard relationship between quadratic forms and bilinear pairing. So, it's a pairing from V cross V into Fp. And how is it defined? You take, well, you just take, if you want to pair two vectors, you take the value of the quadratic form and the sum, and you subtract its value at V and W. Okay, so in terms of all this, now I can also define the orthogonal complement of a subspace. So if V is an FP subspace in V, well, what do you think Z perp is going to mean? You can probably guess. It's just the set of, you just take all the vectors that are perpendicular to everything in Z. So it's such that VZ is 0 for all Z and Z. Okay, and now Z is called isotropic if the quadratic form restricted to Z is 0. And then Z is is called maximal isotropic. Or sometimes also called Lagrangian, then that's holds if, well, both Q should, well, first of all, it should be isotropic, but also it should equal its own perp. So okay, so what does this mean? If the quadratic form is 0 on the space, that means that the inner product, this bilinear pairing is also going to be 0 on that space on Z, and that means that Z is contained in Z perp. And if you say that Z is equal to Z perp, that means that Z perp is not any bigger than Z, which means it's impossible to add anything more to Z and to keep it isotropic. So that's the reason for that definition. And you might actually wonder why both of these conditions are here. Because it's almost true that the second condition implies the first. Because the second condition tells you that if you pair anything, any two vectors in Z, you're going to get 0. And it's almost true that from that, you can go backwards from the bilinear pairing to Q, except that only works in characteristic not 2. And so it's only in characteristic 2 that you need this extra condition about the quadratic form. Okay, in fact, at some point I'm gonna switch to just talk about odd P, just so I don't have to worry about the difference between quadratic forms and bilinear forms. Okay, so that's so by the way, maybe I could say, it's easy to figure out what the dimension of any maximal isotropic space is, because when you take the perp always has the complementary dimension, because this is a non-degenerate bilinear pairing. So in order for Z to equal Z perp, the dimension would have to be half of the ambient dimension. So it'd have to be, and we started with something that was dimension 2n, so that means that any one of these is going to have dimension n. Okay. Now, let me just do one example. So what's an example of one of these maximal isotropic subspaces inside this V with this Q? So one example is you just take the vector space that has sort of the first half of V. So you take all the vectors of this type where the xi are anything in FP. So that's an n-dimensional subspace, and it's pretty easy to see that that's going to be maximal isotropic because, well, first of all, the quadratic form is 0 on all those vectors if you evaluate this function on all those points, and also you can calculate the perp, and yeah, the perp is equal to itself. So yeah, so that's an example of. But there are many others. There's another obvious one where you take the second half, but there's more than that too. So I'll denote OGR, which I'll pronounce ogre of FP. Yeah, I could have started with a dimension space of dimension 2 times E instead of 2 times N if I wanted to. But no, I won't do that. So this is just the set of all possible maximal isotropic subspaces of this fixed V. So I take all the Z's in V. Okay, so it's just a set for now. And the reason for this notation is that ogre stands for orthogonal Grassmannian. So the Grassmannian would classify all, say, for example, the Grassmannian of n, you could talk about the Grassmannian of the parameter as all n-dimensional subspaces of this V. And this O has this extra orthogonal condition that it has something to do with the quadratic form. So okay, anyway, so that's just the notation. Now here's a random process you could do with maximal isotropic subspaces. Choose 2 of them at random and look at their relative positions. So by the way, it's really boring if you just choose 1 at random, because, well, if any one of them looks like any other one, in fact, there's the automorphism group of the quadratic space, which is called the orthogonal group, that preserves the quadratic form, and that acts transitively on this ogre. So it means that, so that there's none of the maximal isotropic spaces look any different from any of the others. as far as the automorphism group is concerned. But if you have two of them, then you can ask about their relative position. And you can talk in particular about the intersection. And the intersection can have different dimension depending on which Z and W you choose. So yeah, so if you choose them at random, you'll get a random variable. That's the dimension of their intersection. So this will have some distribution as you vary the Z and W. And if you wanted to, you could also just choose one of you could just fix the W and just let the other one be random. That would be the same thing because of the transitivity. So okay, anyway, so now I can tell you what the big conjecture is. So this is a conjecture due to myself and Eric Rains of Caltech, so from 2012. So how does this connect to elliptic curves now? So remember back here, we were asking about the P-Selmer group. Yeah, back here. We were asking what does the P-Selmer group of an elliptic curve look like? In particular, what's the chance that its dimension is a given integer s? So I'm now going to give you a conjectural answer to this question. So the conjecture is that for each s, for each non-negative integer s that could be the dimension, the density of elliptic curves. So I'll write this just to remind you. We're looking at all elliptic curves and asking among those, what's the probability that the P-Selmer group has dimension s? And the prediction of this conjecture is that you take this random process that just is involving linear algebra. You take the probability that this intersection is s-dimensional, and then you take the limit as the ambient dimension goes to infinity. Okay, so yeah, so that's the conjecture, and so it's saying that these distributions that you get from this random maximal symmetric subspaces, it tends to a limit as n goes to infinity. And yeah, so maybe I can show you. Well, let's see. Can I show you this formula? So why did we make this conjecture? Well, this is maybe I should just. Okay, let's see if this works. So if I show you, well, okay, is that too small? It's okay. All right. Oh, I could zoom in. Oh, maybe I'll. Okay, but then I have to zoom. I have to also know how to zoom out. So let's see. If I go, like this. Okay. Well, okay. No, that's not so good. So, how does this work? Well, okay. Well, okay. I guess that's about good. Okay, so here's this is the conjecture again. Yeah. So what am I want to tell you about this? So Heath Brown back in the 1990s proved a theorem about the distribution of two Selmer groups of elliptic curves. Now his situation was a little bit different in that he wasn't looking at all elliptic curves over Q. He was looking at the special family where he takes this particular, this is like the congruent number curve, and then take quadratic twists of that curve. And that's a little bit different because for this one you have, well, all these twists, they will have all the two torsion points being rational. And the two torsion points, they contribute to the E of Q mod 2E of Q. And so because of that, they also contribute to all the Selmer groups. So you get a bonus in the Selmer group. You get a plus, well, in the dimension, you get a +2 in the dimension. So instead of looking at the dimension of the Selmer group, it's natural to subtract off the bonus and to look at actual, so that's what this S of E is defining. So really, instead of, this is really, it's more or less looking at the dimension of the Selmer, the Selmer group, except we've subtracted off the boring part. And then the question is, what's the distribution of that? And he found an exact formula. He proved an exact formula that was this number here. So this is defining a certain, I mean, this is something that depends on S, and it gives you a probability distribution on the natural numbers. And so, well, so Eric Rains and I were wondering, well, there can't be that many ways that you can make a random vector space over FP. And so let's just think of all the ways we can make a random vector space over FP and hope that one of them comes out to be the same as that distribution. And so we just kept trying things and we found one that worked. So, and first we got one that was worked at every prime except for 2. And then we thought, oh, we must be getting close. And then, yeah, okay, anyway. So we were trying to explain that formula, and so this is the guess. But we had no reason that at that point we had no reason that elliptic curves should have anything to do with maximal isotropic subspaces. So the next thing I want to say is, okay, so let's now go back to. So we're trying to now, why should such a conjecture be true from the point of view of the arithmetic of elliptic curves? So the goal now is going to be to explain that without just saying, oh, well, look, they gave the same, it gives the same formula that Heath Brown got. Oh, yeah. See, I knew I was going to get in trouble. So I need to zoom out. Okay, now we have the goal. So, okay. So the goal is this, to prove that the Selmer group itself it actually is an intersection of maximal isotropic subspaces. In an infinite dimensional. I mean, here we were taking a 2n dimensional quadratic space and letting n tend to infinity. But the actual thing is that it's an intersection in an infinite dimensional quadratic space. So now the question is, where does this quadratic space come from? I mean, I need to build it just from the elliptic curve. Okay, so I'm going to assume for this that just to simplify things, I'm going to assume that p is odd. I mean, the arguments work also for even p, but then you have to worry. Yeah, so this is for simplicity. And as I said before, the nice thing about this is that the quadratic form is essentially contains the same information as a symmetric bilinear form. So I already showed you how to go from the Q to the symmetric bilinear form just by taking the form that sends v comma w to q of v plus w minus q v minus q w, and you can go the other way too. If you have the symmetric bilinear form, you define q of v to be 1/2 q of 1/2 of v paired with itself, and well, you can see why I want p to be odd now. So if I want this to make sense. So okay, that's just the standard way of going back and forth between quadratic forms and symmetric bilinear forms. And so, all right, so now I have to somehow cook up a quadratic form on, well, first off, I have to cook a vector space, and then I have to cook up a quadratic form on that and say that somehow, actually, and then I have to cook up 2 maximal isotropic subspaces and say that the P Selmer group is the intersection of those. So in order to do this, I'm going to first start with a construction for local fields. Okay, so I'll start with an elliptic curve now over a local field. And my space on which the quadratic form will live is going to be the H1 of the P torsion. So this turns out to be a finite dimensional, this thing is a finite dimensional FP vector space. And okay, now how do I build a quadratic form on this? Well, I'm going to use the Weil pairing. So you have the Weil pairing for an elliptic curve is a pairing that goes between the P torsion and itself and takes values in the multiplicative group. So I'll just write GM, but you should really, if you want, you can think of this as just being QV bar across the multiplicative group of the algebraic closure. Okay, and this Weil pairing induces a pairing on a cup product pairing on the H1s. So you'll get a pairing which I'll call the symmetric bilinear pairing V on this vector space, where you take the cup product. The cup product takes you into H2 of, if the cup product on this thing, taken with itself, lands in H2 of QV with values in EP tensor EP. And then from there, you can go onwards to H2 of QV GM via the Bay pairing. And that's also called the Brouwer group of the local field. And the Brouwer group for a local field is always contained in Q mod Z. In fact, it's always equal to Q mod Z, except for the Archimedean places where it's like, well, if V is the real place, then it's 1/2 Z mod Z. But anyway, so it's always contained there, which you can also embed, if you want to, you can embed that in R mod Z. So this defines a symmetric bilinear pairing taking values in R mod Z. And it's symmetric, even though E is sort of anti-symmetric. That's because, well, E is anti-symmetric, but the cup product also is sort of anti-symmetric. So they kind of cancel out, and they get a symmetric pairing. Yeah. So and then you can that will correspond to some quadratic form because we're doing this for odd P. So you'll get a quadratic form defined on this vector space. Well, it's an R mod Z valued quadratic form. Okay. And now, given that, you can now define. I can also define a subspace, WV, which is the image of E of QV. It's the image of the local points under the map we were talking about at the very beginning. So you have the map from this coming from the long exact sequence of cohomology. So that image, that's going to be a subspace. So yeah, so this thing is just VV again. And so this WV is a subspace of V. And it turns out that this is actually equal to what you get if you take H1 of ZV for EP. And then there's a theorem of Cathy O'Neill that says that that it follows from Tate local duality. So don't worry if you don't know what this is, but it's something about the Galois cohomology of local fields. And from this you deduce that this WV is a maximal isotropic subspace in this VV. Is maximal isotropic in VV with this quadratic form. Okay, so that's it for what happens over a local field. So we've built some vector space with a quadratic form on it, and now we're going to put this together for all the different local fields and to do something for global fields. Well, actually, there's only one global field I'm talking about, which is Q. So global field. Okay. So now we're going to take elliptic curve over Q. So now we're in the actual situation we want to study. So now you build one of these vector spaces, one of these quadratic spaces for each completion. So you let VV be as before, it's the H1 QV of the P torsion of this elliptic curve. And what do you do with all these vector spaces? Well, you put them all together. So you make a big product of all these. So take all these VVs and take the product. And actually, I'm going to take the restricted direct product of the VVs relative to these WVs, these half-dimensional subspaces inside those. So and that whole thing will be one big V. Let's make it a little bit bigger. All right. So there. Okay. So there it's. So yeah. So this is. And I'll denote this by, this is what I earlier called H1 of Adele's comma EP. This group has already appeared. Actually, it was in that diagram I had when I was defining the Selmer group. So yeah, in fact, let me copy that diagram that I had when I was defining the Selmer group. So I'll copy part of it. There was the global H1, which is part of the original horizontal row when I was defining there would have been an E of Q mod and E of Q mod P E of Q here, mapping to this. And then there's this vertical map called beta going down to H1, this thing I've just called V, the adelic analog. And then there is also what comes from the local points, which is E of Adele's mod P E of Adele's. And then this map was called alpha. Yeah, and this one is the same thing this is what I just defined to be V. Okay, so now here's the main theorem. So the theorem is, well, I have this big thing. Oh, actually, this big space also has a quadratic form on it. Can you guess how I'm going to get a quadratic form on this? You define it this way. You take the sum of all the little quadratic. I mean, each little VV has a quadratic form, so you just add them up. Add up the values. And so that gives you an R mod Z quadratic form, or R mod Z valued form on V. And this makes sense on any given element because by the definition of restricted direct product, if you take an element of V, most of the V coordinates will lie in WV. And WV was isotropic. So that means the little QV will vanish on that WV. So most of the terms in this sum, when you evaluate on any element, will be 0. So it makes sense. Okay, so now you have this humongous infinite dimensional FP vector space with a quadratic, an R mod Z valued quadratic form on it. And, well, the first part of the theorem is that if you take the images of these two maps, image of alpha and the image of beta, inside the images of these two maps, that they're both maximal isotropic. The second part of the theorem is that the map beta is injective. And the final part, which is really just a consequence of the first two parts, is that when you take the intersection of these two maximal isotropic subgroups, well, but actually this is just by definition, it's the same thing as the image, the beta applied to this P-Selmer group. Because the Selmer group was the subgroup of things here, such that when you map them down, they end up in the image of this one. So that's the same thing as saying that the elements here, well, that the image of the Selmer group is going to be the things that lie in both images. So yeah, but if beta is injective, then this group is actually just isomorphic to the P-Selmer group itself. So if you put all this together, this is saying that the P-Selmer group is this intersection of maximal isotropic subspaces. Okay, so let me end today. Oh, oops. Okay, so let me just say, I'll just say, well, I'm not going to prove this. I'm just going to list what the ingredients are, and I can tell you more sort of offline if you want to know. So the ingredients of the proof are, I'll just list them. So first of all, for part A, well, I mean the image of alpha is just the direct product of the WVs, and that's sort of isotropic by definition, and maximal isotropic by definition, because each of the WVs was maximal isotropic. And how about image of beta? Why is that a maximal isotropic? Well, that's not so easy, but well, you have to use some global duality theorems for Galois cohomology of global fields. And the particular thing you need is, well, this is going to sound awful, but anyway, there's this thing called the Poitou-Tate sequence, which has an exact sequence with 9 terms in it, and you look right in the middle of that exact sequence, and then it tells you exactly that image of beta is maximal isotropic. So that's the 9-term Poitou-Tate exact sequence. Okay, well, just accept that, and then the last thing, well, then the injectivity. This is something that actually fails if you replace P by a larger, like P squared, or if you replace the elliptic curve by an abelian variety. It involves the Chebyshev density theorem, but the subtle part is that it also involves a very particular fact about elliptic curves, that if you take the CELOS, or not really about elliptic curves, but about the group that come from them. If you take GL2FP, and you take the P-low-C subgroup of that, then that's a cyclic group, and that goes into the proof. And that's something that fails if you, for example, if you take GL4 or GSP4 of FP, then that'll fail then. Yeah, and then C is just by definition, by AB and by definition. Okay, so that ends my talk today, and so next, my last talk, I will talk about how this extends to looking not just at P-Selmer groups, but at the P to the infinity Selmer group. And the great thing about that is that, well, the P to the infinity Selmer group tells you not just about it doesn't just give you an upper bound on the rank. It actually tells you It gives you a precise prediction on what the rank of the elliptic curve should actually be, and also tell you things about the complete Tate-Shaffer average group. Okay, so I'll end here. So I'll see you all tomorrow.